HLAA probability and statistics, day number 2. Today we're going to talk about the multiplication rule, some combinatorics, and the repetition rule. In case this topic seems foreign, it won't after you see the first couple of examples, as we're going to talk about combinations and permutations. So let's go ahead and get started. Okay, the multiplication rule is a form of a permutation. And we'll get into the formula for the permutation in just a moment. But the multiplication rule is for scenarios where n consecutive choices are made, and each choice has x sub I options. So the total number of possible outcomes would be the product of each of the number of choices, each of the options for n choices. So it'll make sense here when we get into an example. For example, you are signing up for one of each of the following courses: science, math, and art. There are 4 science classes, 3 math classes, and 6 art classes. How many possible schedules are possible? I got a little happy there with the word possible. So in this case, n is going to be equal to 3. Okay, there are 3 different courses that we're choosing from, or course disciplines, I guess you could say. Disciplines. Okay, of the first choice we have, or the first discipline, we have 4 science classes. The second discipline, we have 3 math classes, and the third discipline, this must be some kind of special school with 6 art classes. Okay, that's fine. And there you have it. So the number of possible schedules would be 4 times 3 times 6, which comes out to be 72 schedules. Okay, so the multiplication rule is pretty straightforward. You're choosing a certain number of items, and within each of those items you have a certain number of options. So example 2, at the local smoothie shop, you must choose one of each of the following ingredients: 1 base, and we'll call that base x sub 1. X sub 1 looks like it has water, fruit, juice, milk, or almond milk. 5 choices. Okay, x sub 2 is some kind of protein substitute, chocolate or vanilla. Okay, x2 has 2 options. 1 fruit, of which you have 6 choices or options. One butter, either almond, peanut, sunflower, or none. So our 4th ingredient has 4 options. And then our final choice is made by what container, so either disposable or reusable. So our 5th decision has 2 options. So how many different smoothie recipes would be possible? We would simply use the product or the multiplication rule and take 5 times 2 times 6 times 4 times 2, which gives us a pretty big number, 384 options. Okay, that is the multiplication rule. It's typically pretty clear when you're going to use the multiplication rule as you go through a series of choices, each of which has a certain number of options. So that's kind of the giveaway on the use of the multiplication rule. Let's go ahead and look at permutations. Okay, permutations are the total number of arrangements of R objects chosen from a group of n objects. Okay, so this word here, arrangements, is a key word. Anytime you see arrangements or orders, or if order matters, right? So with permutations, order matters. Okay, we're going to use this formula. This is the formula NPR. So N items chosen R at a time. Okay, the formula is as follows: N factorial over N minus R factorial. So this really is just the multiplication rule. Right, so if you took NPN, that would be equal to N factorial over N minus N factorial, which is 0 factorial, which is equal to 1. So this would just be N factorial. So this is the multiplication rule, right? Expanded, that would be N times N minus 1 times N minus 2, right? We're just multiplying N items all the way down to 1. It's really just the multiplication rule expanded, in essence, in its purest form. Okay, so example, 10 people race in the 100-meter dash. How many different top 3 finishes are possible? Okay, so for this, we're going to take 10 permutations of 3. So that'll be 10 factorial. Oh, Apple Pencil just died. Back in a minute. Okay, that would be 10 factorial over 10 minus 3 factorial, which is 7 factorial. Okay, which will come out to be 10 times 9 times 8. Now, let me show you where the rest of this went. Alright, if I divide by 7 factorial, you'll notice that by definition, the remaining portion of 10 factorial reduces out, and we say, see you later. So that would be 10 times 9 times 8, which is equal to 720. 720 different top 3 finishes. Now, you might be asking, how's it possible that that's true? Well, that's a lot of different finishes. Well, Bob finishes first, Ellen finishes second, and Tommy finishes third is a different top 3 finish than Bob, Tommy, Ellen, or Ellen, Bob, Tommy, or Ellen, Tommy, Bob, or Tom, Ellen, Bobby, or Tom, Bob, Ellen. So just those 3 alone, right? Just those 3 alone have 6 top 3 finishes. So that'll show you the magnitude of, like, let's just take one person out of there, right? And throw Carl in there. So Bob drops out of the top 3, Carl's back in, 6 more of those. So you can see how that number is going to increase greatly at a very quick rate. Therefore, the arrangements mean order mattering. Now, if this was a combination, if this was 10C3, which we'll see on the next page, we're then going to take n factorial over n minus r factorial over r factorial, which means that all of these just become one group finish, top 3 group finish. So what will happen is we're going to divide everything by r factorial. Well, 3 factorial is equal to 6. So we're going to take all of these groups, we're going to divide them by 6 because we're only counting this as 1. So if we were just to talk about this same example, instead of top 3 finishes, right, where order matters, if this was one group, right, we would divide our answer by 6. In combinations, there would just be 120 top 3 combinations, as opposed to 720 top 3 permutations. All right, we'll get into more combinations in a moment. Another example, 12 people run for public office. The positions are president, vice president, secretary, and treasurer. Now think about this. Does it matter who gets what position? Yes, because it would be different if someone else got president as opposed to the first time through. So this is another example of permutation where order, or I guess you could say title, matters. So we're going to take 12 permutations of 4, right? 4 positions, 12 candidates running. That'll be 12 factorial over 12 minus 4 factorial, which is 8 factorial, which is equivalent to 12 times 11 times 10 times 9. So that many ways, well, that's a lot of ways. That's 11,880 different political teams. Okay, let's continue on with combinations on the next slide. Okay, as mentioned before, permutations are typically referred to with the term arrangements. Combinations are referred to with the term groups. So if you ever see groups as a key word, you're likely working with a combination. Okay, and you can see here, like we noted on the slide before, n combinations, a group of n, I should probably just read it, of R objects chosen, a group of R objects chosen from a group of n objects. I stumbled over myself there. Let's see if I can figure it out here in this example. You have won a local radio station contest, okay, and apparently received 5 tickets to a concert, of which you will be taking one of them. Out of your 250 friends on social media, you can take 4, right? Clearly, you have 1 ticket for yourself. How many different groups could be selected? Now, it doesn't matter which friend is picked first, right, or which friend is picked fourth. They don't know that. They just know they've been picked. Doesn't assign them a seat, doesn't assign them a title, nothing like that. So let's go ahead and calculate this by taking 250 friends and choosing 4 of them. Okay, we have talked about Pascal's triangle in the past, right? I could go down to the 250th row of Pascal's triangle and over to the 4th. Actually, I guess it'd be the 5th, because it'd be choose 0, 1, 2, 3, 4. So you go to the 5th number in that row. I don't want to go that far. That ain't going to work. So I'm going to use math here. I'm going to take 250 factorial and divide it by 250 minus 4, which is 246 factorial. And then I also have to divide by 4 factorial. All right, this number comes out to be actually extremely ridiculous. So, interesting example picked by Mr. Ludd here. But there are 158,882,700 and I can't read. Yep, 780 different groups of 4 that you could take to this concert. Better be something good, something old school. Guns N' Roses or Styx, Journey, something like that. Okay, let's continue with more on combinations, permutations, and I believe we're going to get into, in this case, repetition. Let's check it out. Okay, repetition rule. If k objects in a group are repeated and identical in every way, the following applies. Okay, I got to explain this. So let's say that you have 10 objects, n equals 10. If, let's say, one of those objects is repeated, so let's say you have a book. In that book, there's 3, I don't know, let's say To Kill a Mockingbird books on a shelf, and they're all identical. Then, you know, that those 3 To Kill a Mockingbird books, in addition to the other, I don't know, however many books on the shelf, would be your total. So let's say there's 10 books. And there's 3 To Kill a Mockingbird books. Well, you would divide by 3 factorial here for the To Kill a Mockingbird books. Then you have 2 dad joke books. And they're both the same. You're planning on giving one away, but they're both the same. Then you would have 2 factorial for the repetition of the dad joke books, and so on. So whenever you get a repetition, you'd put that factorial in the denominator. Now, this isn't a formal definition. This is me trying to explain this to the best of my ability. Let's take a look at an example. How How many ways can you arrange an orange, 2 apples, and a banana if the apples are identical in every way, which is impossible, but whatever, just for this problem, let's do it. So I have 4 pieces of fruit. So that would be 4 factorial, which is 24 different ways to organize those 4 pieces of fruit. Now there's only 1 orange, so I don't have to do this, but I would put 1 here, right? Which wouldn't change our value. But because the 2 apples are identical, every arrangement that I have, I'm going to divide by 2 because I don't know which apple is which, right? So because they're identical, I'm going to divide by 2 factorial, which is 2. And then for the banana, again, just 1. So this would be 24 divided by 2. So there's 12 arrangements of these 4 pieces of fruit. Now, if the apples are not identical, then I can't divide by 2. Okay, so let's look at another example. 3 science books, 4 music books, and 2 homework booklets are on a shelf. How many different ways can these books be organized if each is identical to its own kind? Okay, so I've got 3 science, 4 music, 2 homework booklets. That's going to be a total of 9 books. Okay, so I could organize them in 9 factorial ways. However, the science books are identical, the music books identical, and the homework booklets also identical. When I do that calculation, I get 362,880 divided by 288. And that comes out to give me 1,260 possible arrangements of those books. Okay, what if all of the books are kept together by subject? Okay, so now I'm not arranging 9 items, right? So I've got science, science, science. I've got music, 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 music. I've got homework, homework. So I'm arranging them and keeping them together. So now I'm going to be just working with 3 items, right? And I don't care about, which music book is which. Oh, that one got moved over here. Those 2 got switched. It doesn't matter. They're identical. Therefore, there are only 6 ways, right, to keep the books of like subject together, provided they are identical, right? I could have, let's just go black to keep it simple. Science, math, homework. I could have science, homework, math. I could have math, science, homework. I could have math, homework, science. Hey, MHS. I could have homework, math, science, and I could have homework, science, math. Since all the subjects are kept together as groups, I wouldn't have to worry about it since all are identical about any of the repetition within the group itself. So there you go, 6 different ways. What if only the science books are kept together? Okay, this is where it gets interesting, okay? So if only the science books are kept together, all I care about is that is 1 item, right? And then the rest are free to move as follows. Math, music, 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 music. I think that's what I was talking about. Yep. Homework, homework. So how many objects are being organized? This would be 1, 2, 3, 4, 5, 6, 7. So I would have 7 objects on the shelf, quote unquote 7 objects. And since the science books are all identical and all in one group, I would just consider that 1 factorial. Then I would have repetition of the music books and repetition of the homework booklets. And therefore, I would end up with 105 possible arrangements in that scenario. Interesting stuff. That is the repetition rule. Let's go to one exam style question and we'll be done for this lesson. All right, exam style question. 3 girls and 4 boys are seated randomly on a straight bench. Now, you might not think that a straight bench is, there's reason to say that, but when you start talking circular arrangements, things get kind of funky, and we're going to get to that later in this chapter. Okay, it says find the probability that the girls sit together and the boys sit together. Okay, so probability in general is the number of successes over the number of possibilities. Okay, so let's talk number of successes first. Okay, so when you think about boys sitting next to girls, right, you're going to either have a group of 3 girls and then a group of 4 boys, or a group of 4 boys and then a group of 3 girls. So really, you're taking 2 objects or 2 groups and finding the number of permutations when you choose 2, right? So girls first, boys second, or boys first, girls second. Now within that, the boys and girls are not identical to each other. Right? I guess unless you're told that there's like identical twins somewhere involved, you have to assume that the 3 girls all look different, have different names, all that stuff. So in addition to 2 permutations of 2, we are going to multiply by the number of ways that within that group of 3 girls they could be arranged, which is 3 factorial, and the number of ways that the 4 boys can be arranged, which is 4 factorial. When I multiply all that out, I get 288 different ways that the boys could sit next to the boys and the girls next to the girls. Okay, now we also have to talk about the number of possible ways that the 7 could be arranged. Okay, so the number of possibilities, well, that would be 7p7, right? So if we have to take total number of successes for this scenario, which is boys with boys, girls with girls, divided by the number of possible ways just to let all 7 sit on the bench. Okay, 7p7 is 7 factorial over 0 factorial, which is 7 factorial, which is 5,040. So the probability of this happening is equal to 288 over 5,040, which reduces to 2/35. Your probability can be written in that form as a ratio or as a decimal to 3 sig figs, which is point, that is 0 and a 5 and a 7 and a 1. Oops, that would be 4 sig figs. There you go. There's a probability that we have 7 kids, 3 girls, 4 boys, were to sit on a straight bench, that they would be seated as girls on one side and boys on the other. All right, guys, that's it for day number 2. See you next time.